let's move to the first talk, which is given by Dr. Emi. Are you here?
Yes, I'm here. Let me share the screen.
That's great.
Great, can you see my screen?
Yes.
Awesome. Hello, everyone. Thank you for inviting me to this International Conference on Embodied Intelligence. I'm Amy Kyungwon. I'm an assistant professor in mechanical engineering at Seoul National University. And today I'll be showing a hybrid gripper that allows a bimanual robot handle deformable objects. This is the preview of the work I'll be sharing today. We developed a high adhesion gripping pad based on hybrid electrostatic gecko-inspired dry adhesives. And by using that, we were able to handle deformable objects by human-robot collaborative gripping and also with a bimanual robot. So there are numerous robotic hands ranging from a simple two-finger gripper to a dexterous hand. And they're great for picking up small objects that are smaller than the size of their hands. But when mobile robots pick up large objects, they often pick up like this. They don't utilize their fingers, but instead they depend on the squeezing force between their arms or between their palms. Then they squeeze even more when they pick up heavy or slippery objects because they rely on friction. So they're applying normal force to overcome the weight of the object. So if the weight is heavier, then you have to apply larger normal force to increase the friction. And if the object is slippery, meaning that the coefficient of friction is small, you have to apply large normal force in order to apply larger force, overcome the weight. This means that it's challenging to apply small force for picking deformable and fragile objects. So instead of relying on friction, we wanted to rely on adhesion. So our goal was to develop a controllable adhesive pad to reduce the squeezing force in order to handle deformable objects. There are several solutions for enhancing adhesion. First is to use suction. Suction, however, performs poorly on porous and rough surfaces, and the system has some weight and complexity. Electrostatic adhesion is more tolerant of surface roughness than suction, but the adhesion that they're generating is pretty small, meaning that there's a limitation to how heavy of an object they can handle. Another technology is gecko-inspired dry adhesives. They can provide high shear adhesion on smooth surfaces, but only on smooth surfaces. So if the surface gets a little bit rough, they perform poorly. So our idea was to combine electrostatic adhesion with gecko-inspired dry adhesives so that the gecko-inspired dry adhesives also work on rough surfaces. Let me briefly explain what gecko-inspired dry adhesives are. They're inspired from the tiny hair of a gecko's foot, and because they have tiny hair, they can get very close to the surface and they can maximize the van der Waals forces, which is the intermolecular attractive force. And inspired from that, the micro wedges are about 100 micrometers tall, and when they're put on the surface, only the tip of the wedges are in contact, as highlighted in blue. But when they're pulled in shear or pushed from the top, the wedges lay over and the contact area increases. And because they have large contact area, they have large overall van der Waals forces, meaning that they have high adhesion. And when we let go of this force, the wedges pop up because they're made of silicone rubber, and the contact area decreases, meaning we have very little adhesion. So we can control the adhesion by applying shear force whenever we need adhesion. So you can see this video that when we're pulling in shear, we get very high adhesion, but when we let go of the force, there's barely any adhesion. However, when the gecko adhesives are on a rough surface, you can see that the significant amount of contact area decreases. And again, the less contact area means less adhesion. So what we can do over here is to apply some normal force so that the wedges conform better to the surface and increase the contact area and therefore can maximize the adhesion. So we wanted to use electrostatic force for applying this normal force. So we combined Gecko-inspired dry adhesives with electrostatic adhesive pad. And by applying voltages to the electrodes, the opposite charges are induced on the surface of the object, and they're attracted, and this electrostatic force pushes the gecko wedges onto the surface, maintaining good contact area. So this has, by combining electrostatic adhesion and gecko-inspired dry adhesives, increases the contact area in macro scale and micro scale. So in macro scale, you can see that by applying electrostatic, we can wrap around an object and increase the overall contact area. And on the right, this is the fabric with texture that you cannot pick up with just the gecko wedges. But when you apply electrostatic, the gecko wedges can conform to the surface texture of the fabric and therefore can pick it up. So there has been groups who tried combining electrostatic adhesion and gecko-inspired adhesive, and we wanted to further increase the adhesion by incorporating doped material and maintaining smooth surface finish of the gecko wedges. So from this typical one material, PDMS material gecko adhesives, we developed bimanual, bi-material hybrid pads. There are three features of the hybrid pad that improve the adhesion. First, we optimized the pattern that provides height and found the pattern, the gap, and the electrode width that gave us the highest adhesion by doing a Coulomb multiphysics simulation. And second, we doped the silicone rubber with high dielectric constant. And by doing that, we were able to further increase the electrostatic force. And this is important because that means that given the same voltage, we can get a much higher electrostatic force. And lastly, instead of doping entire gecko wedges with the doped material, we left the tips and the surface of the wedges to be PDMS. And that was important because we were able to maintain the good surface finish and sharp tips of the gecko wedges, as you see in this microscopic picture. And this is important because you have to get very close to the surface and maintain good contact area in order to maximize the van der Waals forces. So you can see that compared to the completely doped material, which has rough surface, the adhesion was much higher. We tested at different voltages at different roughness surfaces, and we were able to get up to 3 times greater adhesion by applying electrostatic adhesion compared to just gecko-inspired dry adhesives. We tested a human-robot collaborative grasping on a paper bag filled with groceries. This is difficult to pick up because this is easily deformable, and gecko adhesive do not stick well on this paper. You can see this close-up video of the electrostatic being in action. You can see that even though the initial contact area was not great, the electrostatic, the pad clings onto the surface and maintains good contact area. We were able to decrease the squeezing force by half. Moving on, we also applied this to a bimanual mobile robot, which had less control of the squeezing force. We designed a gripper for this digit robots. We designed different mechanisms. We incorporated different mechanisms to conform to the object surface in macro scale, mesoscale, and micro scale. And we were able to maximize the contact area, meaning that we were able to maximize the adhesion. We tested the gripper on different roughnesses, and we were measuring the squeezing force. And for this testing, we didn't compare it with the digits bare hand because the digits bare hand was really not working that well. So we covered it with neoprene so that we made it better and then compare that with our hybrid pad. Even so, we were able to get up to 10 times smaller force when we were using our hybrid pad, utilizing electrostatic force and gecko-inspired dry adhesives, compared to a digit hand covered in neoprene. This is a video of the digit robot picking up objects. I'll skip to the main part. This is the digits original manipulator. So we didn't even put the neoprene here. And you can see that it's really not great at picking up slippery objects and deformable objects. We control the distance between the hands, and then we decrease the distance until the robot was able to lift the object off from the surface. And you can see that even if it deforms a lot, it ends up slipping off from the hand or rotating from the hand. But with our gripper, the hybrid gripper, we were able to reliably grip the same deformable objects and even a bag of rice. All right, I'll skip the summary due to the limited time. Thank you for listening, and I'll stay until the panel discussion.
Thank you very much. It was very, very impressive to know that how the gecko inspired mechanism can be implemented in the robot. Thank you so much. Okay, then let's move to the